Tonight, we're beginning with a question that sounds simple at first, and then becomes much larger the longer you sit with it. If a spacecraft left Earth in 2026 and kept moving outward, how long would it really take to get beyond the Milky Way? By the end of tonight, you will understand why the answer becomes so enormous so quickly. Why a galaxy is not the kind of thing you simply travel across the way. You might cross a country or even a solar system. And why escaping it means stepping into a scale that pushes far beyond ordinary human thinking. And if space questions like this are the kind that pull you in, feel free to subscribe, because that's exactly what we explore here. At first, the idea feels almost clean. You leave Earth, point away from the crowded inner regions of the galaxy, and keep going until home is behind you. That picture makes sense for a few seconds. But the moment we try to attach a real speed to that journey, the size of the problem starts to show itself. One of the fastest spacecraft human beings have ever sent into deep space is Voyager 1. It is moving at about 17 kilometers per second relative to the Sun. That is an astonishing speed by human standards. It is fast enough to cross huge distances in the solar system, fast enough to leave the planets far behind, and fast enough to feel almost unreal when compared with anything we build for life on Earth. But inside the Milky Way, that speed begins to shrink. Our galaxy is not a small neighborhood of stars. It is a vast system, tens of thousands of light years wide, from where we are to anything that might begin to feel like the outside. And a light year is already almost too large to picture comfortably. It is about 9.46 trillion kilometers. Once distances begin stacking in the tens of thousands of light years, the mind naturally starts to lose its grip. So it helps to say the answer plainly, early. If we left in 2026 using the kind of speed human beings can actually achieve today, escaping the Milky Way would take hundreds of millions of years. That is the first anchor. Not centuries, not a few thousand years, hundreds of millions. That means the journey belongs to a span of time so large that normal travel language starts to sound misplaced. This would not feel like a voyage in the usual sense. It would feel more like deep history. If a spacecraft had begun such a trip when dinosaurs were still alive on Earth, it still would not be finished today. Continents would shift. Species would appear and vanish. Oceans would change. Entire chapters of Earth's story would come and go while the ship kept moving through the dark. And what makes this even more striking is that this first answer is still only a rough one. Because so far, we have treated the problem in the simplest possible way. We have imagined the Milky Way as a distance to cross, as though escaping it only means choosing a direction and moving far enough outward. That gives us a real starting point, and it is useful because it lets us feel the scale almost immediately. But the galaxy is more than a distance problem. The Milky Way is a physical system with structure, mass, motion, and gravity. We are already inside that system, moving with it. Our Sun is orbiting through the galaxy right now, carrying Earth and every human life along with it. So leaving the Milky Way is not like walking out of a room or sailing off the edge of a map. It means trying to get beyond something vast that has been holding us the entire time. That is why the number grows so large so fast. Even before we carefully define what counts as outside, even before we ask where the galaxy truly ends, even before we deal with gravity in any serious way, the journey is already operating on a timescale that barely fits inside human imagination. And that is what makes the question so worth exploring. Because once we know the first answer, the deeper mystery begins to open. What exactly are we trying to leave behind when we say the Milky Way? That is the point where the number begins to change shape. At first, hundreds of millions of years can sound like the kind of phrase people use when they simply mean very, very long. It can pass through the mind as a dramatic number without fully settling anywhere. But once we give it something to rest against, something human, it starts to feel different. Recorded human history reaches back only a few thousand years. The pyramids of Egypt are old by our standards. Ancient Rome feels distant. The earliest cities feel like the deep past. Entire religions, empires, languages, and ways of life have risen and fallen inside a span that is tiny, compared with the travel time we are talking about here. If a spacecraft left Earth and needed hundreds of millions of years to finish its journey, then all of recorded history would fit inside that trip, like a small opening chapter. Everything we usually call old would become recent. The whole story of farming, writing, kings, trade, war, science, industry, and modern life would barely begin to measure the length of that motion through space. The names we know best would disappear almost immediately into the background. The longest-lasting buildings would crumble. Nations would change shape again and again. Even the languages used to launch the mission would almost certainly vanish long before the craft had traveled more than a small fraction of the full distance. And then there is the human body itself. A long human life might reach 80 or 90 years. Some lives end much earlier. A few stretch past 100. But even the longest life is only a tiny flicker beside a journey lasting hundreds of millions of years. A person could not meaningfully take such a trip in the ordinary sense. No crew could board a ship, look ahead toward a distant goal, and expect to arrive. The timescale is so large that the word traveler starts to lose its familiar meaning. If such a mission were ever attempted with present-day speeds, it would belong less to individuals than to chains of inheritance. Generation after generation would be born into it and vanish inside it. And even that picture may still feel too human, too small, because the number reaches beyond civilization and begins to overlap with the history of life itself. Hundreds of millions of years is long enough for entire groups of living things to appear, spread, change, and disappear. It is long enough for the surface of Earth to become unfamiliar. Long enough for coastlines to shift and climates to transform. Long enough for the world that launched the mission to become something no one on board could recognize, if anyone was somehow still there to compare it. A useful way to feel that scale is to place it beside the age of the dinosaurs. The dinosaurs lived long before us, and yet they do not belong to the beginning of Earth's story. They are one chapter in a planet that is more than 4.5 billion years old. Some of the great dinosaurs vanished about 66 million years ago. So when we say a journey might take hundreds of millions of years, we are speaking about spans of time several times larger than the distance between us and the last day of the dinosaurs. That is not ordinary distance with a few extra zeros added. That is distance expanding until it begins to behave like time on a planetary scale. And this is why the opening estimate matters so much. It is easy to hear a large number and assume it is just there for effect. But once we bring it down into history, lifetime, and memory, it stops sounding exaggerated. It starts sounding almost severe in its honesty. The Milky Way is so large that human beings become brief almost immediately. Our best machines, which seem bold and impressive near Earth, are reduced to something closer to a slow drift once they are measured against a galaxy. That feeling can be a little unsettling. We are used to asking how long something will take and expecting the answer to remain inside the world of practical thought. Days, months, years, maybe even decades. Here, the answer steps outside that world almost at once. It enters a range where the trip is no longer just difficult. It becomes detached from the ordinary rhythm of human continuity. And yet, even now, we are still standing at the edge of a deeper idea. Because all of this depends on what we mean by the Milky Way in the first place. The number feels overwhelming already, but it comes from a rough first picture, a simple image of a galaxy as a vast region you move through until you are finally beyond it. That picture is useful, but only as a beginning. To understand why escape becomes so difficult so quickly, we need to know what the Milky Way actually is. To understand why the journey becomes so extreme, it helps to stop picturing the Milky Way as a soft band of light and begin picturing it as a real place. On a clear, dark night, far from city lights, the Milky Way looks like a pale river spread across the sky. For most of human history, that glowing band was all anyone could see. It looked beautiful, mysterious, and distant, but it did not yet look like something with shape. It did not look like a system you could be inside. Now we know that the Milky Way is a galaxy, and a galaxy is not just a loose scattering of stars. It is a huge organized structure held together by gravity. It has a broad disk, spiral arms, a crowded central region, and a vast outer reach that stretches much farther than the bright part most people imagine when they hear the name. That disk is the part that gives the Milky Way much of its familiar form. If you could rise far above the galaxy and look down on it, you would not see a straight band at all. You would see a great spinning disk of stars, gas, and dust, shaped somewhat like a flattened whirlpool. Curving through that disk are spiral arms, long sweeping regions where stars, clouds, and darker lanes of dust help give the galaxy its graceful shape. Our view from Earth is strange because we are inside that disk rather than above it. We are looking through the crowded plane of the galaxy from within, which is why the Milky Way stretches across the sky as a glowing strip, instead of appearing as a full spiral. It is the difference between looking at a forest from above and standing deep among the trees. From the ground, the full shape disappears. You see only layers, distance, and density. At the center of the Milky Way, the galaxy grows thicker and brighter. This region is called the bulge. It is packed with many more stars than the quieter part of the disk, where our solar system lives. Deep in that central region sits a supermassive black hole called Sagittarius A star. It does not swallow the whole galaxy the way people sometimes imagine, but it marks the crowded, powerful heart of the system. Around the disk and central bulge, the galaxy also has a much larger surrounding region called the halo. This is where the Milky Way begins to feel less like a bright spinning city of stars and more like a vast, thin outer domain. The halo contains some stars, clusters of stars, hot gas, and most importantly, much of the galaxy's hidden mass. That hidden mass matters because the Milky Way is not made only of what shines. A great deal of its gravity comes from dark matter, which does not glow, but still helps shape the galaxy and hold it together. That means the Milky Way is larger than it looks. The bright part, the part most people picture first, is only the most visible region. Beyond that glowing disk is a wider structure, and beyond the most obvious stars is still more of the galaxy's reach. So the Milky Way is not a flat picture pasted onto the sky. It is layered. It has a denser middle, a broad spinning body, and a more extended outer region that becomes harder to see but no less important. This changes the feeling of the question almost immediately. Once the Milky Way becomes a place with structure, the journey no longer feels like heading toward a simple edge. It starts to feel like moving through a system with depth, shape, and hidden extent. The glowing band we see at night is only one view from one position inside something much larger. And that inside part matters. We are not looking at the Milky Way from a safe distance. We are living within it. The sun, the planets, the dust of Earth, every ocean, every city, every living thing, all exist as part of this larger galactic structure. The Milky Way is our cosmic environment in the same way Earth is our planetary one. We are inside its disk, moving with it, surrounded by its stars and held by its gravity, whether we notice it or not. That is where the image begins to sharpen. The Milky Way is no longer just something overhead. It becomes the enormous system around us, above us, below us, and far beyond us. It becomes the setting of the journey itself. And once that setting is real, the next question becomes much more precise. If this galaxy has a shape, a center, a disk, and a wider reach beyond the bright stars, where exactly are we inside it? Once the Milky Way begins to feel like a real place, the next thing we need to know is where we are inside it. That matters more than it may seem at first. If Earth were sitting near the outer edge of the galaxy, then leaving might sound difficult, but still somewhat straightforward. We would already be close to the boundary. We could imagine turning outward and beginning the final stretch. But that is not where we are. The solar system lives well inside the Milky Way. We are not near the bright, crowded center, which is filled with many more stars and much stronger galactic density. But we are also nowhere near being outside the galaxy. We sit in the disk, inside one of the spiral arms, at a distance of about 26,000 light-years from the galactic center. That places us in a middle region, far from the heart, but still deep within the larger structure. A helpful way to picture this is to imagine living inside a vast city. You do not live downtown, in the most crowded and intense part of it, but you also do not live at the last quiet house on the edge of town, where the road simply ends and open land begins. You live somewhere out in the city, in a place that may feel less dense than the center, but is still firmly part of the whole system. To leave, you still have a very long way to go. That is our situation in the Milky Way. The galaxy's disk is often described as being around 100,000 light-years across, though the exact number depends on what part of the galaxy we mean and where we draw its brighter limits. From where the Sun is located, the distance inward to the center is already immense. The distance outward to the visible outer regions is also immense. There is no sense in which we are almost there. We are starting from inside, and that simple fact shapes everything. Our position also helps explain why the Milky Way looks the way it does from Earth. Because we are inside the disk, looking along it, we see many more stars spread across that flattened galactic plane. That is why the Milky Way appears as a glowing band across the sky, rather than a distant spiral shape. We are seeing our local view from within the structure itself, surrounded by stars in some directions more densely than others, with dust clouds blocking portions of the light and making the band look uneven and textured. So even our night sky quietly tells the truth about our position. We are embedded in the system. We are not standing outside it, looking back with a clear map in hand. We are inside the moving disk, orbiting with the Sun, seeing only the local view from a small and ordinary place in one spiral arm. And the Sun is moving too. Our solar system is not parked in one spot. It is orbiting around the galactic center at an enormous speed, taking roughly 225 to 250 million years to complete one full orbit. Sometimes this is called a cosmic year or galactic year. That means that since the dinosaurs disappeared about 66 million years ago, the Sun has not even completed one full lap around the center of the Milky Way. That is another useful anchor. We often think of galaxies as still pictures, as if stars are fixed in place and we are simply choosing where to go within them. But our starting point is already in motion. Earth, the Sun, and the rest of the solar system are all being carried around inside the galaxy as part of its larger flow. So the journey outward does not begin from a quiet, motionless platform. It begins from a moving location inside a rotating system. That deepens the challenge in a subtle way. Leaving the Milky Way is not just about aiming away from the center and heading off into darkness. It means starting from a position that is already far inside the galaxy, already bound to its motion, and already separated from anything like an outer edge by distances so large they are hard to hold in the mind for long. This is why the opening number grew so quickly. It was not only because the galaxy itself is large, it was also because we are starting from within it, from a place that feels local to us only because it is home. Home can make scale feel smaller than it really is. But once we step back and look at our true position, the shape of the problem becomes much more serious. We are not preparing for a short climb out of the galaxy. We are preparing, at least in thought, for an outward journey from deep inside a structure vast enough to make even our starting point feel remote. And once that starting point is clear, the next question follows almost automatically. How far is it from where we are to anything that could honestly count as outside? Once our position is clear, the next step is to give the journey a shape. It is one thing to say we want to move outward from the Milky Way. It is another thing to ask how far outward that really is. Without a distance, the idea remains loose. It feels like pointing into darkness and saying somewhere over there. But space becomes much easier to understand once direction turns into distance. From where the solar system sits, about 26,000 light-years from the galactic center, the path outward to the brighter edge of the Milky Way is not a short final stretch. It is still a journey of tens of thousands of light-years. That point is worth sitting with for a moment. A single light-year is the distance light travels in 1 year, moving at about 300,000 kilometers every second. Light is so fast that it can go around Earth more than 7 times in a single second. And yet, even with that speed, it still takes over 4 years for light to reach the nearest star system beyond our own. So when we begin stacking distances in the tens of thousands of light years, we are moving into a range that no ordinary form of travel language was designed to handle. From our region of the galaxy, heading outward through the disk toward the farther visible reaches means crossing something like 20,000 to 30,000 light years, depending on the exact direction and where we choose to treat the bright outer galaxy as beginning to thin away. That gives the problem a real span. We are no longer imagining a vague departure from home. We are imagining a trek across a meaningful fraction of the Milky Way itself. This is where the geometry of the situation starts to matter. The Milky Way is often pictured from above as a broad spiral disk. If you place the center in the middle and then mark the sun partway out from that center, you can begin to see the challenge clearly. We are not at the hub, and we are not near the rim. We are somewhere between them. To reach the outer visible parts, we would need to move across a large slice of the galaxy's width. To go farther still, beyond the familiar body of stars, would mean continuing past that bright disk into more remote territory. So the journey has direction, but it also has depth. It is not a matter of rising a little above the galactic plane and suddenly being free. If we are speaking in broad, understandable terms, escape begins as a very long outward crossing from an interior position toward the Milky Way's far side. And because our starting point is already so deep within the system, even the first part of that movement is enormous. A helpful comparison is to imagine standing in the middle region of a continent and deciding to walk to the shore. If you are already near the coast, the sea feels close, even if the walk is tiring. But if you are far inland, then the same idea becomes something much larger. The coast is still real, still reachable in theory, but it belongs to a different scale of travel. That is what happens here. The word outside sounds simple because it feels like it should describe a nearby boundary. Yet from where we are, outside the Milky Way begins only after crossing distances so large that the galaxy must first become a map in the mind. You need to picture a center behind us, outer regions ahead of us, and our own small location between those two extremes. Once you do that, the trip stops feeling like a loose cosmic thought and starts to feel like a line drawn across a giant structure. And that line is long. Even at the speed of light, crossing 20,000 or 30,000 light years would take 20,000 or 30,000 years. That alone tells us something powerful. Light itself, the fastest thing we know, does not treat this as a short journey. So any human-made object moving far more slowly immediately inherits that difficulty in a much harsher form. This is why the first estimate landed in such deep time. The destination was never just a point somewhere in the dark. It was always a vast outward span from an interior location to a distant boundary that is itself not easy to define. And that last detail matters more than it first appears. Because once the Milky Way becomes a real distance to cross, a new uncertainty rises almost immediately. We can measure our position. We can picture the broad path outward. We can estimate the span to the visible outer regions. But a galaxy is not a wall, and it does not end like a road. So before we can say what it really means to get beyond it, we have to ask a more careful question. Where does the Milky Way actually stop? That is where the journey becomes a little more subtle. A distance can be measured. A direction can be drawn. But an edge is a different kind of thing. We are used to edges that behave clearly. A coastline separates land from sea. A wall separates one room from another. Even the atmosphere of Earth, though gradual in some ways, feels like it gives way to space with a recognizable change. The Milky Way does not offer that kind of ending. When people picture a galaxy, they often imagine a bright spiral with a visible outer rim, as though the stars simply stop at a certain point, and the rest is empty. From far away, that image can be useful. It helps the eye understand the general shape. But once we ask where the galaxy truly stops, the answer becomes less tidy. The bright disk has an outer reach where stars become fewer, and the clear spiral structure begins to thin. If you were looking at the Milky Way from a great distance, this brighter body would be the first thing you noticed. It would feel natural to call that the galaxy. In that sense, one possible meaning of leaving the Milky Way would be to travel beyond the main visible disk, far enough that the dense, glowing body of stars is behind you. That is a reasonable first idea, but galaxies are not made only of the parts that shine most clearly. Beyond the brighter disk, the Milky Way continues in thinner and less obvious ways. There are older stars scattered farther out. There are globular clusters orbiting in the wider surroundings. There is hot gas extending beyond the main body. And there is the much larger dark matter halo, a broad region of hidden mass that does not glow but still helps shape the galaxy and hold it together. So if someone says they have left the Milky Way because they are beyond the obvious spiral body, that may be visually true in one sense. The galaxy would no longer surround them as a dense field of stars in the same way. The bright disk would have fallen behind. The view might already feel lonely and remote. But visually outside and physically outside are not always the same thing. That distinction matters because it changes the meaning of the journey. If we are satisfied with leaving the bright, familiar body of the galaxy, then the target is one thing. If we mean leaving every important part of the Milky Way's larger structure, then the target moves farther outward. And if we mean escaping the galaxy in the deepest physical sense, then the question may have less to do with visible boundaries at all, and more to do with gravity. This is what makes the Milky Way such a strange destination. It has layers of ending. There is the point where the bright disk begins to thin. There is the broader region where stars become much more sparse. There is the halo, where the galaxy still has presence even when it no longer looks like the familiar Milky Way of photographs and diagrams. And surrounding all of this is a larger gravitational reach that does not announce itself to the eye. So the word outside begins to split into several meanings. A traveler could move beyond the bright spiral body and feel outside in an ordinary visual sense. The galaxy would no longer appear as a place they are immersed in. It would begin to look more like an object behind them. That experience would be real. It would matter. It would mark a change. Yet the deeper story would remain unfinished. Because space does not care only about what looks finished to us. A galaxy is not merely a picture. It is a system. It extends beyond its brightest parts, and some of its most important boundaries are not boundaries in the usual sense at all. They are gradual transitions, fading structures, and invisible influence. That makes the destination fuzzier, but also more interesting. The problem is no longer just how far we must go. It becomes which version of departure we mean. Are we trying to leave the crowded visible galaxy behind? Are we trying to pass beyond the broader stellar body? Or are we trying to become truly free of the Milky Way as a physical system? Those are not identical goals. And once that becomes clear, the journey changes shape again. A simple outward line across the disk is still useful, but now it begins to feel like only the first layer of the story. Leaving the visible galaxy might be dramatic and meaningful, but it may still fall short of the deeper kind of escape we are really trying to understand. Because a galaxy can still hold you long after it stops looking like home. And that leads to the next question almost naturally. If we move beyond the visible part of the Milky Way, have we truly escaped at all? That deeper kind of escape begins with a quiet correction. A ship can travel a very long way from the familiar stars and still not be free. From a human point of view, that may sound strange at first. We are used to thinking visually. If a traveler leaves the bright part of a city behind, then they have left the city. If a plane crosses beyond the coastline, then it has left the land. Our eyes are often good enough to tell us when a boundary has been crossed. A galaxy is more deceptive than that. The bright disk of the Milky Way is the part that announces itself most clearly. It is where stars are packed more densely, where dust lanes cut through the light, and where the galaxy looks full and richly structured. If a spacecraft kept moving outward long enough, there would come a point where that dense brightness began to thin away. The sky behind the ship would still contain stars, but the Milky Way would no longer feel like a glowing world wrapped all around the traveler in the same way. The galaxy would begin to look more distant, more contained, more like something being left behind. That would feel like departure. And in one sense, it would be. But physical escape asks a different question. It asks whether the spacecraft has moved far enough and fast enough that the Milky Way can no longer pull it back as part of its own system. That is a much stricter idea. It means that distance alone is not enough. A ship can be very far away and still remain gravitationally bound, still following a path that belongs to the galaxy, rather than truly breaking free from it. This is easier to understand if we start closer to home. Think about Earth and the Moon. A spacecraft can rise far above Earth's surface and still be in Earth's gravitational grip. It may be high enough that our planet looks smaller, high enough that the atmosphere is gone and the darkness of space surrounds it. But none of that means escape has happened. To actually leave Earth behind, the spacecraft needs enough speed to overcome Earth's pull. The same logic works at the scale of the solar system. A probe can travel far from the Sun and still remain part of the Sun's wider gravitational domain. The Milky Way works the same way, only on a vastly larger scale. The galaxy is not just a collection of visible stars scattered through darkness. It is a gravitational system with enormous mass. That mass includes the stars we can see, the gas and dust spread through the disk, and the much larger dark matter halo extending far beyond the bright spiral structure. All of that mass helps shape the galaxy's pull. So even if a spacecraft moves beyond most of the bright disk, it may still be deep inside the Milky Way's larger grip. This changes the meaning of the journey in a powerful way. Leaving the visible galaxy may create the feeling of escape, but the feeling is not the same as the physics. The stars could be thinning. The disk could be shrinking behind the ship. The traveler might look back and see the Milky Way as a more contained object in the sky. And still, the craft could remain part of the galaxy's story, still moving through space on terms the galaxy has set. That is the quiet turning point in the question. The first version of leaving was based on sight. It asked how far we would need to go until the Milky Way no longer looked like the environment around us. This newer version is based on freedom. It asks when the galaxy loses its hold over the ship's motion itself. Those are two very different thresholds. One is about appearance. The other is about whether you still belong to the system you are trying to leave. Once that difference is clear, the journey feels more serious again. The visible disk, vast as it is, becomes only one layer of the challenge. A ship might cross that layer and still not be truly outside in the deeper physical sense. The Milky Way can continue beyond what the eye finds obvious, and its influence can continue beyond what the mind first pictures. So the question becomes more exact. We are no longer asking only how far it is to the thinning edge of the stars. We are asking what kind of motion would finally carry a spacecraft beyond the Milky Way's control. We are asking what it really means to stop orbiting within the system and begin moving independently of it. And that kind of escape depends on something more than distance. It depends on speed. That is where the journey stops being only a matter of miles or light years and becomes something deeper. A ship does not truly escape the Milky Way just by drifting far enough away from the bright stars. It escapes when the galaxy no longer owns its path. That idea sits at the heart of the whole problem. Gravity is not simply a force that pulls things straight inward like a rope. In large systems, it shapes motion. It decides which objects remain bound, which ones orbit, and which ones finally move with enough freedom to leave. Earth circles the Sun because the Sun's gravity holds it in a long curved path. The Moon circles Earth for the same reason. Our solar system itself moves within the Milky Way because the galaxy's mass is shaping our motion too. So when we ask what it would take to leave the Milky Way for real, we are really asking when a spacecraft stops being one more object moving under the galaxy's grip. That depends on velocity. If a spacecraft starts from our region of the galaxy and simply heads outward at too low a speed, it may travel for an enormous distance and still remain bound. Its path may stretch far into the outer parts of the Milky Way, but the galaxy would still be shaping that motion. In time, the craft might slow, curve, or remain part of a very long galactic trajectory, rather than becoming truly free of the system. That is the deeper rule. distance tells us how far the trip extends. Velocity tells us whether the trip counts as escape at all. A helpful way to picture this is to imagine throwing a ball upward from Earth. If you toss it gently, it rises and falls back. If you launch it harder, it climbs higher before falling. If you launch it fast enough, it never returns. The first two throws differ in height, but they are both still under Earth's control. The third reaches escape velocity. That is the threshold where the path stops belonging to Earth. Galactic escape works on the same principle, only at a far greater scale. The Milky Way is full of mass. There are hundreds of billions of stars, enormous clouds of gas and dust, and a dark matter halo reaching far beyond the part of the galaxy we can easily see. All of that mass contributes to the galaxy's gravity. That means escaping the Milky Way is not about finding the place where the stars become sparse and stepping beyond it like crossing a border. It is about moving fast enough that the galaxy can no longer keep you as part of its larger motion. This is why the problem becomes more demanding the more carefully we define it. A ship might make the Milky Way look smaller behind it. It might enter darker regions where the dense disk has faded into a more distant structure. And still, from the galaxy's point of view, it could remain bound. It would still belong to the system in the same basic way a comet can travel far from the sun and yet still remain part of the solar system. That comparison helps because it shows how misleading appearances can be. A comet at great distance may feel almost gone, but gravity has a longer memory than our eyes do. The Milky Way works that way too. Its visible body may fall away, while its influence continues. So the real barrier is not the last bright patch of stars. The real barrier is the speed needed to break free from the galaxy's hold. That is what turns this from a giant road trip into a physical threshold. Once velocity enters the story, the question becomes sharper and in some ways harsher. We are no longer only asking how long it takes to cross a great span. We are asking whether our motion is enough to escape a system built from vast amounts of mass. And that changes how we think about our own place in the galaxy as well. The sun is already moving around the Milky Way at a tremendous speed, carrying Earth with it. We do not notice it in daily life, but we are already part of a larger galactic flow. A spacecraft leaving from Earth does not begin from rest in some quiet cosmic stillness. It begins inside an active moving system, and any true escape must overcome the fact that we are already bound into that motion from the start. So the question narrows into something more exact. How much speed does a spacecraft actually need if it wants to leave the Milky Way in the deepest physical sense? Not just pass beyond the brightest stars, but truly stop belonging to the galaxy's pull. Here is where the problem becomes more demanding than it first appeared. Up to this point, it has been possible to imagine the Milky Way as a huge distance that could, in theory, be worn down with patience. If the galaxy is large enough, then perhaps escape is simply a matter of continuing outward for long enough. But once gravity and motion enter the picture fully, patience stops being the main issue. A ship does not earn freedom just by spending a long time traveling. It has to be moving fast enough for the galaxy to truly lose its hold. And that required speed is very high. The exact number depends on how the Milky Way's mass is modeled, especially the part we cannot see directly, like the dark matter halo surrounding the galaxy. But from our part of the Milky Way, astronomers estimate that escape requires a speed on the order of about 500 to 600 kilometers per second relative to the galaxy. A commonly cited value is around 550 kilometers per second. That is the kind of number that changes the whole mood of the journey. 550 kilometers per second means covering about 33,000 kilometers every minute. It means crossing a distance roughly equal to Earth's circumference in a little over 1 minute. It means moving at nearly 2 million kilometers per hour. By human standards, it is almost absurdly fast. And yet, in galactic terms, it is simply the speed needed to stop belonging to the Milky Way as a bound object. This does not mean a ship must fire its engines forever at exactly that speed, as though aiming for a magical line in space. It means that if the craft's total motion through the galaxy is below the escape threshold, then however far it wanders outward, it still remains part of the Milky Way's larger gravitational story. It has traveled far, but it has not broken free. A useful way to picture this is to imagine a deep valley. If you roll a ball uphill gently, it may travel a surprising distance before slowing and turning back. Roll it harder, and it climbs farther. But unless it has enough energy to clear the valley entirely, it still belongs to the valley. Galactic escape works the same way. A spacecraft can move outward through a vast stretch of space and still never truly leave if it lacks the speed needed to rise beyond the galaxy's gravitational depth. That idea makes the challenge feel more exact. The Milky Way is no longer just a region with a center and an outer edge. It is a system with a threshold. Below that threshold, motion remains trapped in one form or another. Above it, escape becomes physically possible. So there is a sense in which the galaxy has two kinds of size. There is the visible size, the one we imagine when we picture stars spread across a spiral disk. And there is the gravitational size, the one expressed through how much speed it takes to get away. The second size is the more serious one. It is also tied to where we begin. We are not launching from empty intergalactic space. We are launching from Earth, carried by the Sun, already moving inside the Milky Way. That means any true escape attempt begins from within a living system of motion. The starting point matters. The speed needed from our region of the galaxy is not a universal number that applies everywhere in the same way. It belongs to where we are, how mass is distributed around us, and how deeply inside the Milky Way we still sit. Once that sinks in, the early estimate from the beginning of the documentary starts to feel almost gentle. At first, the trip seemed overwhelming because the distance was so large. Now the trip becomes even harsher because distance was only half the problem. A ship could head outward across astonishing spans of space and still fail in the deeper sense if it never crossed the escape speed threshold. The galaxy would still, in its own quiet way, be keeping the ship. That is what makes this more than simple travel math. It is the difference between wandering far from home and actually ceasing to belong to home's gravitational pull. One is a matter of scenery, the other is a matter of physics, and physics is less forgiving than appearances. So the question sharpens again. If the Milky Way asks for something like 550 kilometers per second from our region in order to truly escape, then how close are we really? What is the fastest speed humanity can actually reach in 2026? And how small does that speed begin to look once we place it beside the galaxy's demand? Once that escape speed is placed beside our own machines, the scale of the gap becomes much easier to feel. Human beings have built remarkable spacecraft. We have sent probes past every major planet in the solar system. We have landed on the moon, touched asteroids, flown through the atmosphere of Titan, and sent instruments beyond the outer planets into interstellar space.